Hints for selected questions of HW2. Part 1. Hints for question number 14 through number 19 of HW2. Yeah. The first one, question number 14. Yeah. We apply the binary search on a 512 element ordered array. How many comparisons do we need for the worst case efficiency? Yeah. So this question looks simple, yeah. But actually, based on my experience before, there are many problems. Yeah. So there are about approximately more than one half, approximately around one half of the students couldn't get the correct answer. Yeah. So let me explain the point. Actually, it is an easy question. It is an easy question. Yeah. But so the problem is here. The problem is, yeah. So let me talk about the main problem here. Okay. All right. Binary search. Yeah. Most people are familiar with the binary search, right? Yeah. So people know how to apply the binary search on an n-element array, n-element ordered array. Yeah, let's say in this way, okay? Ordered array. Yeah, so the general question. Now, this question, we need to look at the worst case efficiency. Yeah. The formula for the worst case efficiency. Okay? Yeah. So what is the formula? It looks easy, right? It's a simple, easy question. Yeah. All right. So here, the problem. Yeah. The main problem here. All right. Some students, they search the web, try to find the answer, and it's very likely. So we know when you search the web for answers, you may get many different forms of the answers. You need to select which one is the correct one. Yeah. Sometimes the answers may not be quite right. Yeah. Here it's an example. Yeah. Yeah. You may find a formula like this. Yeah. Log base 2 of n. Right? Yeah. So it's very likely you may get this answer. Yeah. All right. But in our notes, when we discussed about this topic, we derived exact formula, actually 2 formulas for the worst case. Yeah. Yeah. So in this class, we have 2 formulas. Yeah. But the formulas you search from the web and our formulas in the notes look different. The problem is here, look different. So why they look different? So this one, yeah, so let me assume, so this one is from the web. Web search, okay? All right. Our formula, yeah, from the notes. Yeah, let's look at the formula from our notes. We have 2 formulas, but they are the same. So if you, you can find, so if you try to go to the right place, yeah, so here I couldn't remember, binary search Module 4, Part B. Okay? Yeah. So the page numbers, part number, I couldn't remember. Yeah, but Part B of Module 4, you can easily find. Yeah. Remember, we use this notation, K max, right? Yeah. The maximum number of comparisons, that's for the worst case. But there are two equivalent forms. One is ceiling function log base 2 of n plus 1 in the parentheses, the first one. The second one, 1 plus floor function log base 2 of n floor function. Yeah. So that's the formula in our notes. Okay? Yeah. So what's the difference? The key difference is here. Yeah. This one, the one you find from the web, we do not say it's wrong. Okay? We do not say it's wrong, but it is an approximate formula. Okay? Not exact. Okay? Approximate formula. There is some small error. Okay? So there is a small error, but the error is not big. Okay? The error is not big. Yeah. The difference is less than 1. There is a small error. So our formula here, we derived exact formulas. Okay? Exact formulas. No error. This one, no error. Okay? All right. To answer this question, you need to apply our exact formulas. One of the two. So anyone is fine. They both should give the same answer. Yeah. And so what's the difference? Yeah. So here, what's the difference? Difference, first you can see this one may not be an integer, right? Yeah. So if n is not a power of 2, it may not be an integer. So then some students, yeah, so they notice that. They notice this may not be an integer. So some students, they make it an integer, but they make it in this way. Okay? Yeah. So they try make it integer. One is the floor function of log base 2 of n. Another is the ceiling function of log base 2 of n. So naturally convert the approximate formula to integer expressions. Yeah. If they do that, you can see different from our exact formula, right? Different at n is power of 2. Yeah. Yeah. Especially when n is power of 2, they are different. Okay? So if n is not a power of 2, then most of the time they could be correct, most of the time, yeah, but not 100%. Yeah. So here you can see the power of 2 usually causes the problem, and here I give you the power of 2 number. 512, it's a power of 2. Okay. So now you understand how to answer this question, right? Yeah. All right, so let's move to the next question. Yeah. All right, yeah, before I move to the next question, just say something, some comments, a little more. So the reason I designed this formula, because for most people, if they didn't learn this, they didn't have the training of this algorithm class on this topic, like us, then those people, it's very likely they do not know the exact formula here. Okay? Now, most people, if they just study by themselves, they may not pick up the detail, this kind of details. Okay? So they just get some approximate formula. Okay? Yeah. So that's from what I know based on my experience. So that's the reason I designed this simple question to check you. So if you pick up the details for students taking this algorithm class, okay? Yeah. So you should be able to do it. Yeah. You know the exact formulas. Okay? Yeah. All right. Yeah. So that's this question. Next one. Question number 15. Given an array with 6 elements, we want to apply the merge sort on this array. How many comparisons do we need for the best case? So let me give you an example here. Let me use a different number. So let me work on a number with different n. So n different from the 6. Okay? Yeah. The 6 you need to do the work for n equals 6. Here I just choose a different n number and to show you how to solve this kind of questions. Yeah. All right. For the best case, we apply our merge operation formula for the best case. We have that. Okay? Yeah. So the basic formula we need to apply for the best case, that is the minimum of n and n. When we merge two ordered arrays with array sizes n and n, so for the best case, we need to use this formula. Yeah. So that's simple. But how to apply this formula? Yeah. So let me show you. Yeah. So one student asked me, what input do you expect? The input. So here we do not know the input, ascending order, descending order, all possible. Yeah. So here the thing is, which one would result in the best case? Then we select that one. Okay? Yeah. So we are targeting the input that would produce the best case. Okay? Whatever it is. Yeah. Before we work, we may not know it. Yeah. At the end, we may know it. Okay? At the end, we may know it. Yeah. So that's one point. Okay? About the input. Another point. Yeah. So when I grade this kind of questions before, I notice another common error. So many students made that error. So the error is like this. Yeah. So here, avoid that. Okay. Apply the standard merge operation in the notes. Okay? Yeah. Yeah. Do not modify. Okay? Do not modify it. Do not modify it. Okay? Yeah. Because some students, they thought about some smart way to get a very good best case efficiency. Yeah. But that way you modify the standard merge sort. For example, yeah, you have A array, A1, AN, and you have another ordered array. So here we assume in ascending order, and the B array, B1, Bn, also in ascending order. All right. So our standard merge sort, we need to compare A1 and the B1 as our first comparison. Okay. That's the standard. But some students, they modify the algorithm in this way. They compare An and the B1 as the first comparison. And assume that An less than B1, because in that way you already get the all the array elements ordered. Yeah. One comparison. Yeah. They can do that. Yeah. So here, do not do in this way. Okay. Yeah. So do not do in this way. Yeah. Yeah. So the reason, let me explain the reason here. The reason, yeah. First, because when we use the standard merge operation implementation, we work on all the possible inputs, right? All the possible inputs. Yeah. Yeah. So we use that way. Yeah. All right. So here the problem. So you do this special way. It performs extremely well on the, on this special case. Yeah. An less than B1. This special, it performs extremely well. Yeah. But if we get a two ordered arrays for the general case, then you mean your way. This you need to use, because you cannot see the data, right? You do not know the data. Yeah. So you need to complete your merge sort in this way, right? Yeah. You need to complete it. Yeah. So then, for the general data, so your merge sort may not perform well. Okay? Yeah. Only for a very, very special case it performs well, but for the general case data, yeah, its performance could be worse, right? Yeah. In general, on average, it could be worse. Yeah. So that's the reason. Okay. So that's the reason we do not make that change. Yeah. Stick to the standard merge sort. Okay. Yeah. Do not modify it. Yeah. So here I do not ask you to modify the merge sort, right? Yeah. So I ask you to apply the merge sort, and then you count the number of comparisons for the best case. So that's what you should do. Okay? Yeah. The reason I spend so much time explaining, because I estimate so many students, quite some students, about 1/3 of the students, based on my impression, got this problem. Okay? They thought, so they are very smart, but not correct. Okay? Yeah. All right, the correct way. So now let me do the correct way. Yeah. So I need to use the space here. Yeah. All right. Let me consider n equals 7. Okay? Yeah. So any number, not necessarily even number. N equals 7. Okay? All right. So let me work on it. Yeah. But when I do the merge, I want to, adopt some special notation to make our work as simple as possible. We need to do the merge work, right? Yeah. The merge work, I do not want to write a lot of sentences, okay? I just use some special notations to represent my working details, okay? Yeah. So what kind of special operations? Yeah. All right. Because when we do the merge, A two arrays, right? Yeah. So A subarray, B subarray, okay? Yeah. So when we do the merge operation here, yeah. Yeah. I want to write this way, okay? Yeah. All right. I use a pair of parentheses to represent the useful information after the merge. Okay? The useful information, because later we may need to use the information. So, yeah, from two places. Yeah. One is merge these two subarrays, the number of operations. What is the number of operations? Yeah. So the first number, parenthesis, the first one is number of comparisons. Okay, the first number. Then I draw vertical bar. The second number, number of total elements. Parenthesis. I use this way, okay? So inside a pair of parentheses, I write two numbers separated by a vertical bar. Okay? Yeah. Because this vertical bar, I have special meaning. Yeah. The way I use this way, yeah. The first number means the number of comparisons we need to merge these two arrays. The second one, after the merge, the total number of elements. That information will be used in the next round. So when we do the merge, we do round by round. The first round, second round, third round, and so on. Okay? All right, so with this notation, now let me show you the work, how to run the merge sort on a 7-element array for the best case. Yeah. All right, yeah. So let's start. When we start, we have an array with 7 elements. 1, 2, 3, 4, 5, 6, 7. Okay, all right. Yeah. So now we split somewhere in the middle, right? Yeah. So for the split, okay, the first split here, the first. So we get 2 subarrays. Okay, the first round split. The second round, these 2 subarrays, second round here, and here the second round. All right, second round. Okay, all right. Then third round, third round, third round. All right. Yeah. So after these 3 rounds of splits, we make each subarray single element subarray, right? So that's the end of all the splits, end of the splits. So that next we can start our merge operations, our standard merge operations, and using the notation here. So our special notation here. Okay, simple special notation here. All right. Yeah. All right. Now, let me do the merge, the first round merge. Yeah. I will, reverse merge, reverse the split order. When we do splitting, we have an order, right? Now the merge order, reverse the splitting order. Okay, all right. Merge these two subarrays, then use our special notation to write it. Okay. What is the number of the first integer? What is the number of comparisons? Apply this formula. Minimum m and n, but the size, here the size is minimum of 1 and 1, right? The first array, 1 element, second array, also 1 element. Minimum of 1 and 1, so that's 1. So that means the number of comparison is here. Okay? Then, the total number of elements, should be m plus n, right? Yeah, 1 plus 1, that's 2. Okay? So after the merge, there are 2 elements. Oh, sorry. Yeah, remember, we use the vertical bar, the special vertical bar, to, try to make a special notation. Okay? Make a special notation. Yeah. All right. Similarly, merge these two adjacent subarrays, 1 vertical bar 2. Okay? Yeah. 1 vertical bar 2. Yeah. And here do nothing. All right? Yeah. Then let's collect a subtotal. Yeah. So in this run, the first run merge subtotal 1 plus 1 plus 1. Sum of the first component of these 3 pair of parentheses. Okay? The first component. Do not use the second components. Okay? Yeah. So 3 comparisons. Okay? So you know the meaning. 3 comparisons. All right. Next round. Yeah. Next one. Merge these 2 adjacent and these 2 adjacent subarrays. But these 2, this time we need to use the number of elements. Now you can see the second components should be used. So that's the reason we need to keep them in a pair of parentheses. Yeah. All right. So the minimum of 2 and 2, that's 2, right? Vertical bar. The sum of 2 and 2, that's 4. Okay? Yeah. Here, because this is 1, right? Yeah. The size is 1 here. Okay? All right. So, and you use size 2 there. The minimum of 2 and 1, right? The size is 1. Yeah. Size is 1. Okay? Yeah. So here, I didn't write the size of 1. Okay? All right. So the minimum, or if you because size is 1, if you want to use our special notation, 0 vertical bar 1, right? Because no comparison. Okay? 0 vertical bar 1. Okay? So the minimum of 1 and 2, that is 1, right? Okay? Vertical bar. The sum of the 2 numbers, that's 3. Okay? All right. Then we calculate the subtotal. Okay? Subtotal equals sum of the first components, 2 plus 1 equals 3. Comparisons. Okay? All right. Then the final round. Merge these 2. Then our last parenthesis. Yeah. Minimum of 4 and 3, right? Minimum of 4 and 3. Yeah. So 3 here. Okay? Sum of 4 and 3, 7. Okay? 7, that's the size of the whole array. Okay? All right. So the subtotal also 3. Okay? Yeah. So at the end, we calculate the total. Equals 3 plus 3 plus 3 equals 9. So that's the answer, final answer, 9 comparisons. For the best case, okay? For the 7-element best case. So after you understand the special way to run the merge sort for the best case, then you can do the similar thing for n equals 6. It should be, pretty easy. Yeah. But n equals 6, when you split the first split 3, 3, right? So then, because you have 6 elements, 1, 2, 3, 4, 5, 6. You split in the middle. So the first split, first 3, 3. So then next, and in the second round and the third. Right? Yeah. So that's the hint for question number 15. Yeah. For next one, we change to the worst case. We use a different formula, but the notation, the way we run the merge sort, the same as what we did here. Yeah. All right, so let me go to the next question. Yeah. This time, n equals 9. Okay, n equals 9, but we should select some n not equal to 9. Okay, yeah. So let me run another example to help you get familiar with the whole process. Yeah. So this time, let's quickly run this example. So I like to pick n equal to 11. How about that? N equal to 11. Yeah. And we run it for the worst case. Yeah. All right, so let's draw array with 11 elements. Okay, all right, the split. Yeah, the split. The first round, the first split, first. Here. Second. Second, split, second, split. All right. The third split, here, third round, split, third round split. Okay, fourth round, yeah, the last one, fourth, here, fourth here, fourth here. Okay, yeah. So then no more. Okay, all right. Now we are ready to run our merge operations round by round. Yeah, our first round. So we just do the reverse way of the splitting order. But this time our formula, so we need to change our formula. Our formula is n plus n minus 1 for the worst case, right? So the worst case, we switch we use this formula. Okay, all right. Now, merge these two, m and m, 1, 1. Yeah. 1, 1. Yeah. 1 plus 1 minus 1. So it's 1. Okay. Parenthesis, the first number comparison is 1. Yeah. Because 1 plus 1 minus 1 is 1. The second, the sum of total number of elements of these two subarrays, that's 2. Okay? All right. And this one, 1 bar 2. Okay? This one, 1 bar 2. All right. Yeah. So the, the fourth. Yeah. We work on the fourth splitting. Okay? Subtotal. 1 plus 1 plus 1 equals 3 comparison. Okay? All right. Next one. Okay? All right. Here, 2, m equals 2, n is 1 element here. 2 plus 1, 3, 3 minus 1, 2 here. 3. Okay, all right. Next one. Yeah. Also 2 bar 3. Vertical bar 3. Yeah. Here, three. Okay. Here, 1, 1. So that's 1 vertical bar 2. Okay. All right. So now the subtotal. 2 plus 2 plus 2 plus 1. Okay. 2 plus 2 plus 2 plus 1 equals 7 comparison. Okay. Yeah. Next round, merge. This time use 3 and 3, m and m. Yeah. 6 plus 6 minus 1, 5. Vertical bar 6. Okay. Here, 3 and 2. 3 plus 2, 5. Minus 1, 4. 4 vertical bar 5. Okay. Subtotal. 5 plus 4 equals 9. Comparisons. Okay. The final round. Yeah. Work on 6, 5, n plus n, 11, 11 minus 1, 10. 10 vertical bar 11. Okay. And the subtotal 10. 10. Okay. Then we calculate total. At the end, the total number is 3 plus 7 plus 9 plus 10 equals 29. Comparison. How about that? Yeah, not too hard, right? Yeah. After you understand, the whole process, so you can do it easily. Okay, the best case and the worst case. Yeah. All right, so that's these two questions. Yeah. Next one, another question related to merge, also for the best case. Yeah. Best case. The formula here, minimum of m and n. Yeah. And array sizes use these 3 different sizes. Yeah. So here, I like to use a general representation. The size of the first order array A, the size of second order array B, and the size of third order array C. Yeah. Yeah. So I show you the idea. Yeah. Because there when we merge three ordered arrays, we have several ways to merge. Okay? We have several ways to merge. Okay? Yeah. And we don't know which way would give us the best solution. The best solution means the number of comparison is the smallest. Okay? The number of comparison. So here, our situation is like this. Our situation is we have several cases. Yeah. Among those cases, we need to select the one with the minimum number of comparisons. Okay? Yeah. That's our general idea. Yeah. All right, so here, let me give you those cases. Now, oh, what's wrong? Yeah. All right. Let me give you the general cases. Okay. Case 1. Okay. Case 1. Yeah. Merge. Yeah. So case 1. Yeah. So here, let me use notation. A comma B. That means we merge two ordered arrays with size A and a size B respectively. Okay? So this is notation. Then, by the best case merge formula, we get minimum of A, B, vertical bar, our older notation, A plus B, right? Yeah. So that's the first merge. Then the second merge, yeah, because after that, our second merge, yeah, so let me use, the same line, okay? All right. Array sizes, the first one, A plus B, comma, C, then our merge result, the minimum of A plus B, comma, C, vertical bar, A plus B plus C. Okay, that's the first case. All right, yeah. Then you calculate the total number of comparison. Calculate, so you know what numbers to add, right? What numbers to add. Find total number of comparisons. All right. Case 2, we do the similar way, but with different merge order. Okay, different merge order. Let's consider A comma C first. How about that? Then you get the minimum of A, C, then A plus C, right? Yeah. Okay. And the next merge A plus C B, the minimum of A plus C comma B vertical bar A plus B plus C. So then you calculate total number of comparisons for this case. So the last case, so you merge B and C first. So you get the minimum B, C, vertical bar B plus C. Next, B plus C and A. So you get a minimum of B plus C, A plus B plus C. Okay? Yeah. So you get a 3 comparison numbers for these 3 cases respectively, right? Then you pick the smallest. The case with the smallest number of comparisons. Okay? Yeah. So this is for the best case. The next question, for the worst case, you only change to the formula. Yeah, so here, the formula for the worst case, n plus n minus 1. Okay? For the worst case. Okay. So you do the same thing. Right? Still, you have A number, B number, and the C number. Okay? Yeah. So case 1, you merge A, B first. So you get the number of comparisons, A plus B minus 1, vertical bar, A plus B. Okay? Yeah. The next step, A plus B, comma, C, and the vertical bar, A plus B plus C minus 1, vertical bar, A plus B plus C. Okay? Yeah. So when you calculate the total, you use these 2 numbers to calculate the total. Okay? Yeah. The total. Subtotal. Yeah, not total. Okay? For this case, subtotal. Yeah. But later we do not add up. Yeah. Yeah. Oh, yeah. It may not be good for the subtotal. Yeah, because confusion. We won't add up these 3 numbers. We pick the smallest one. The best solution should have the smallest comparison number. Yeah, so that's called a total 1. Total 1 equals A plus B minus 1 plus A plus B plus C minus 1. Okay? Then, case 2, A, C, A plus C minus 1, A plus C. Then A plus C merge with B, a resize, A plus B plus C minus 1, A plus B plus C. Okay? All right. Case 3, B and C merge first. Yeah. B plus C minus 1 bar B plus C. Next, B plus C A plus B plus C minus 1, vertical bar A plus B plus C. Okay? So then you compare, at the end, compare and get the minimum of total 1, total 2, and a total 3. Okay, that's this question. Okay, all right. Next one, number 19. Yeah, number 19. The main step, how to derive a recurrence relation. That's the key part. After you find that recurrence relation, then it's very easy to, calculate this expression, the value for this expression. Yeah. But when we calculate recurrence relation, here we need to do a special operation here. Okay? All right, so what's that special operation? Yeah. Do this operation. The first one, S sub n multiply another one, S squared plus 1 over, phi squared. Okay, so this is the expression Sn. This is the expression S1, right? Yeah. So when n equals to 1, so you have this expression. Sn times S1. Yeah. Let's do the expansion. So phi 2n plus 2 plus another term, phi 1 over phi to the 2n also plus 2. And another one, phi 2n minus 2 plus phi 1 over phi 2n minus 2. Okay, so what is this expression based on our function, not function, our definition, Sn plus 1, right? Sn plus 1. What is this expression? Sn minus 1, right? Yeah. So now you get a recurrence relation. S1 times Sn equals Sn plus 1 plus Sn minus 1. Yeah. But for the recurrence relation, we should write the expression with the largest subscript, Sn plus 1 at the left hand side, and S1 Sn minus Sn minus 1 at the right hand side, right? Yeah. So this recurrence relation. Yeah. S1, you can find it. You can find it easily, right? Yeah. You know how to find it. So after you get the S1, so you have this recurrence relation explicitly. Then can you apply it to calculate this expression? Yeah. That's this, how to solve this question number 19. Yeah. All right, yeah, so that's the first part.